started. Basically, you know, obviously we're sort of catching up over the last 8 years from 2013, but we're going to focus more on the present developments. So let me start with the general overview. Basically, you guys are generally familiar with the dense plasma focus. The whole question in the dense plasma focus is how do we get off of the yield plateau? The plasma focus historically had a very fast scaling current to the fourth power of yield, which was very optimistic. But as you got beyond 1 megamp, all of a sudden that scaling turned into a plateau. And if you see our FF1 results, which are very good compared with all the other results, they were on the scaling line, but we too fell off it as we passed 1 megamp. So that's the basic overall goal, is to get back onto that scaling, which could lead us to a net energy production. So one way to look at the fusion yield, we and many other people think that the fusion is occurring in a plasmoid, which is self-confined by the magnetic fields produced through a series of instabilities in the current itself. So if you take the normal formula for yield, n squared, volume, tau, and a function of temperature, which is the cross-section reaction rate term, well, by doing just a little algebraic manipulation, you get this formula, which is n goes as A, the number of loops in this plasmoid, times the current mu to the 1/2 divided by the alphane velocity times the radius all squared. If we assume the tau, the confinement time, goes approximately as R, and there is a lot of experimental evidence and also theoretical reasons to believe this is true, then you get that yield goes as I to the 4th, as A to the 4th, and this term is basically a constant. In other words, the alphane velocity in these plasmoids doesn't vary a lot. So a way of looking at the compression is increasing the number of loops in this plasmoid. And you get a big return for, you know, you get a big bang for the buck here. So the working hypotheses that we originally had back in 2013, 2014, is that high Z impurities at the start of the pulse cause early oscillations in the current, leading to the destruction of the filaments. The loss of the filaments causes lower plasmoid density, less twist in the plasmoid, lower density, yielding, leading to lower yield, about 10 times below that scaling law. So back in 2014 and 2015, we were moving to the first step, which was to change the electrodes to a monolithic design. So there would be no arcing between parts of the electrodes inside the vacuum chamber, and to use tungsten instead of copper. to reduce the impurities. Well, in 2015, when we started those experiments, we found that tungsten has major oxidation problems. And the tungsten oxide is a very fragile material, breaks down very easily. And that led to an increase, not a decrease, in impurities. So in 2016, we did major improvements in these monolithic tungsten electrodes. Syed suggestion, we lengthened the chamber so we would have less splashback from the ion beam. We consulted with our colleagues in other fusion efforts, and we got some good advice on how to bake out the chamber to get rid of the oxygen clinging to it and the water clinging to it. We used a titanium nitride coating on all of the steel parts because we found that stainless is a great source of oxygen. And finally, we used pre-ionization, a steady microamp glow discharge. Strictly speaking, it's a dark discharge to eliminate the runaway electrons, which we had good evidence was causing an increase in erosion and impurities right at the start of the pulse. So we got really good results as a result of all these changes. So this table summarizes that our yield increased by 50% over any other DPF operating at the current we were at, 1.1 megamp. We got twice as much fusion as any other DPF operating at our input energy, our stored energy of 60 kilojoule. And we got a spectacular record confined ion energy, which we published in Physics of Plasma. We confirmed it measured by time of flight, and we confirmed that it was really confined. The neutrons were emitted isotropically. So we could also see that more energy was going into the pinch. This is the high voltage probe at the time of the pinch is 0 nanoseconds. And you can see tungsten gives a lot more energy into the pinch, a lot higher peak voltage than copper. So as of 5 years ago, we achieved the highest confined ion energy of any fusion device. And in the discussion, we can talk more about some of the data for that. We got 2/3 of the highest wall plug efficiency with DD. And we got far higher wall plug than any other private fusion effort. And in the 5 years since then, this situation really hasn't changed. So our results were really close in terms of wall plug efficiency with pure deuterium to the large government experiments. So this is JET, which is still the record holder in this parameter. This was our Focus Fusion 1 experiment, Z Machine, NIF, and EAST. And obviously, our project cost was a great deal less than any of theirs. The way we have presented this to investors is percentage of deuterium burned, which is sort of a easier to understand stand-in for the n-tau T parameter. And we compare this with the other private efforts that have actually reported fusion. Most of them haven't reported any fusion. And you can see we're about a factor of 100,000 ahead of the best funded fusion effort, private fusion effort, which is TAE, and way ahead of general fusion. So, okay, I think a slide got missing here, but to summarize the results, all right, well, I'll have to give it to you orally. You have seen it in the papers. We basically got a density of around 3 to 6 times 10 to the 18th per cubic centimeter, a confinement time of about 30 nanoseconds, and as you saw, the mean ion energy about 250 keV. So at that point, we started preparations for using the beryllium electrodes. Now, during that period where we were preparing for the beryllium electrodes and waiting for them to arrive, we tried without success to get the oxygen off of the tungsten entirely, which proved extremely difficult. So we weren't really able to get a bare tungsten electrode. So in 2019, we were able to move on to the first experiments with beryllium electrodes. So let me just pause here. Do people want to ask some questions here, or should I go on to cover the recent experiments?
I had what I think are a couple of quick questions, Eric, if I might.
Okay.
That threshold you run into, could that have to do with you get up to high enough current that the I²R heating at the electrode is giving you more impurities?
Well, the overall problem obviously is precisely that with our machine and other high current machines, you are getting, more intense current. Now, by itself, the electrodes should be able to take it, but there are ways that that current effect concentrates itself. And one way we know of was the runaway electrons that occur at the start if there's no pre-ionization. So pre-ionization mitigates it. The other way, which I'll get into in the rest of the presentation, I'll mention in the rest of the presentation, is when you get to the other end where you have the pinch, obviously, the better your pinch, the more X-rays you get and the more heating. So in both cases, yeah, you are battering your electrodes more, and that leads to more impurities. Now, moving on into the second section, the big advantage of beryllium is your impurities are very low Z impurities, much lower than with tungsten.
Eric, have you thought about putting, I won't say coating, but something like graphene on the surface of the tungsten to reduce the impurity levels? A
lot of people have raised, graphene. The problem with graphene at the moment is that its conductivity is extremely anisotropic. So if you pick a direction, you can get it to act as a decent conductor. But in the other two directions, it will be basically a poor conductor. So ultimately, it would be vaporized pretty quickly. Now, people are working on the idea, well, since not with graphene, I'm sorry, but with nanotubes, why can't you just get a mesh, a three-dimensional mesh of nanotubes, so you can have nanotubes running in all three dimensions, and therefore you get a high conductivity material. And that's a great idea, but nobody succeeded in doing it. So at the moment, we don't have any coatings available that would have the very high conductivity that we would need. But I will get into at a later point whether we might, when we get to boron, produce a natural coating. But I'll get into that later on. Okay, any other quick questions, and then we'll go on to beryllium. Okay, so we renamed our device Focus Fusion 2B for boron and beryllium. So we started with beryllium electrodes, 10 centimeters long, kept the anode radius the same at 2.8, and we took the first shot June 4th, 2019, so just almost exactly 2 years ago. And we did, in fact, achieve the first goal. We showed spectroscopically that the only elements that could be observed were deuterium, the fill gas, beryllium, and oxygen. So the beryllium lines are these three big lines off to the left. Oxygen is this little line here, and most of the rest, almost all the rest, is either deuterium or molecular deuterium. And we did measurements that we had achieved low impurity, low erosion operation. The reduction of oxygen compared with the tungsten was about 20-fold. We were getting 40 times less impurities by mass, and into the sheath, we were getting at least 100 times less Fc squared, which is obviously a measure of the impact of the impurities on the plasma. Now, I'm not sure that this is convincing. We had to take a picture of the beryllium inside the glove box, so the lighting's a little different. But this tungsten, after 200 shots, was quite rough. And especially you could see this is the area right next to the insulator where the pulse starts. It was quite eroded. And if you look at the beryllium after the same number of shots, very close, it's actually still smooth. It now has a matte finish rather than a shiny finish. And there's very little erosion. Some parts of it are still actually quite shiny right next to the insulator. So we did achieve that goal. But what we saw was still the disruption of the filaments. So let me just I want to stop this little GIF. So thanks to Syed's hard work with our ICCD camera, we were able to take a series of images at different times on different shots with very consistent conditions that showed how the filaments were being disrupted. So this is a view from the side, and we're looking through a gap in between the anode, the cathode veins. So this big black object is a cathode vein. So the pulse is starting here from the insulator, and you first see the single bright line of the sheath. But as this starts at about 200 nanoseconds, as we get beyond 200 nanoseconds, you see something happening and the sheath looks double. And as it moves forward, you can see much more clearly that this is the leading edge. And you have a very disorganized pattern here. You still seem to have filaments, but you have them very disorganized. A bright line, which I interpret as a shock wave, and then behind that, the very well organized filaments that we see in smaller devices. So this part, of course, that's very disorganized and disrupted is the part that goes into the pinch. So we can see that the problem is we need to get rid of this disruption. So I'm going to go back to the So what's the possible cause? Well, we said current oscillations were caused by the impurities, but we got rid of the impurities, but we still had the oscillations. So clearly the oscillations, and this are strong oscillations in the rate of rise of the current, still could be causing the shock wave and the disruption of the filaments. So I couldn't resist adding this morning. I got this on the internet this morning. This is an image from the tokamak mast, M-A-S-T, in the UK, which shows their bugaboo, the ELM, which of course is nothing more than a filamentation instability. So we're worried about our device disrupting the filaments. They're worried about the filaments disrupting their device. So it took a very long time for our tokamak colleagues to come to the conclusion that they really did have filaments, but they do know that now.
Yeah. Eric, if I may add though, the mast and elm is at the surface, and it's a sort of MHD instability that's filamenting it. It's not intrinsic to the spherical torus's main current. That's how the elms work. We have a fairly big group working on related things at Wisconsin.
But I mean, I haven't seen images like this before. The elm takes the form, the energy is concentrated in a filamentary shape.
Yeah, my understanding is it goes unstable at the edge and it peels off. In fact, some of these modes are called peeling modes. Mm-hmm. I can point you at people who know much better about it than I do. While we're on the filaments, though, if I may ask a quick question.
Sure.
Your scaling goes with the number of loops, but for a given power, doesn't the more loops you have, the less power going into a given filament and therefore less temperature, or?
No. As far as, okay, let me just go back. As far as we can see, the filamentation is determined by the conditions at the start of the pulse. So let me just escape again. Okay, so basically you can see that there's about, let's say, 10 filaments between each vein. Well, that's not what we imposed. We have little teeth on the cathode, but there are only 2 teeth between each vein. So I interpret that this is a Rayleigh-Taylor instability that is determining the spacing of these filaments. When you get, if the filaments got to the end in this regular array, what I would expect is that the kink instability would tie them up into quite a tight plasmoid with probably something like 6 twists in the solenoid, like formation at the center of the plasmoid. With this disorganized array, you get much less concentration, because obviously these filaments aren't arriving at the center at the same time, and they've become quite dispersed. So the kink instability does not have the ability to tie the thing up as tightly as if it was a regular symmetric array. That's my current hypothesis. So, okay, to go back.
Eric?
Yeah.
Quick question. You see the disruption occurring when you have the shock. Now, there is a possibility that the Rayleigh-Taylor instability with the large ion gyro radius, which occurred like the empty experiments, it occurred in some opening switches, occurs there. Have you really looked at that? At the shock front, rather than early on. I understand the Rayleigh-Taylor early on. This the large ion gyro radius.
The filaments are not small compared with the ion gyro radius. The ion gyro radius, remember, they have not heated up very significantly. The filaments at that point are, well, we don't know from our own experiments, but other experiments have indicated they're about at no more than 20 or 30 EV at this point. So the ion gyro radius is pretty small. Now in the shock, yeah, of course, we don't know the conditions. We don't know for certain that that is a shock. That's an interpretation of the images, that it looks like a shock. And in other experiments with other devices, people have shown that you can get this perpendicular shock that disrupts an array of filaments. So what is happening within the shock? You're right, I don't know. Our goal is to see whether we can get rid of the shock. That pattern does not occur in the smaller devices. the smaller DPFs, you see a very regular array of filaments proceeding right to the pinch. So at the moment, we're trying to get rid of the shock. Let me just, so let me continue and then we can go back to this.
If you can get rid of the shock, it's a different story. But if you have the shock, you've got to worry about the Rayleigh-Taylor there.
Right, absolutely. Okay, so unfortunately, while we were doing these experiments, we ran into an additional problem. This was coincidental with the onset of the pandemic. But right in March, when we were about to resume firing, we saw that the anode had a crack in it. In fact, it had two cracks. So you can see one crack here and the other crack there. So we became really worried about why we were overstressing this anode. And we also found that inside the anode, we had this very even array of ripples. So we thought to ourselves, well, is the beryllium actually melting? Which takes quite a bit of heat to do so. Beryllium, one of the advantages of the beryllium is that it has a very high heat capacity for a metal. Well, we looked at simulations, and the simulation showed very clearly that the stress expected on the beryllium would greatly exceed the yield stress at temperatures much less than the melting temperature. So we would expect a cracked surface, not a rippled surface. But I found in the literature very interesting experiments, which were confirmed by other researchers, that if, beryllium is fairly brittle. If you bend it slowly, it bends. If you hit it hard, it breaks. Well, it turns out if you hit it really hard, if you have an extremely high rate of increase of strain, it loses its strength entirely. The solid beryllium flows like a liquid without melting. So this is a very convenient and very interesting property that was discovered only recently in 2015 using explosives, actually, as the source of the sudden stress. And our stress onset is just in the range that they were looking at. So our interpretation is that the beryllium was actually relieving its stress by doing this rippling. So now we get into the present phase. So what happened was we realized in March of 2020, we had to shut down because of the pandemic. We had to shut down because of the broken anode. So we said, well, why don't we upgrade to what we were intending to do, which is to increase the current by reducing the induction by moving to dual switches. The main source of the induction is the spark gap switches. So our ultimate goal is to move from 1.2 megamps all the way up to 2.4 megamps with 24 spark gap switches. Now we're not there yet. We're taking an intermediate step of going with 8 capacitors and 16 spark gap switches, which is already a great deal of work. So we did a lot of simulations to reduce the stress, and we found that the best way was to increase the radius of the hole. This was also partially inspired by experimental work done by our colleagues at Lawrence Livermore. And they found that the erosion of a copper electrode decreased as the radius of the hole increased and the thickness of the walls decreased. So we calculated that the largest source of stress is heating by X-rays from the background plasma. The X-rays from the plasmoid are very high energy, and with beryllium, they pass either totally through the beryllium or so deeply into it that their energy is dispersed. But the low energy X-rays from the background plasma are absorbed in a very thin layer. So with a small anode, the force actually increases as I to the fourth, again, over r cubed. That's the radius of the hole, not the radius of the anode. So this is a little simulation. This shows about 1,000-fold increase in movement with the half cross section of an anode that has the thickness of our old anode. So you see, here's the pulse hitting, and you get deformation, obviously, as I say, greatly exaggerated, and the stresses go up as high as 3 times the yield stress. When we go to a thinner wall, and it's not the thinness of the wall, it's the fact we're getting away from the source, bigger hole, then the stress is reduced by about 70%. And you can't read the top of the scale, but it's, take my word for it, the top of the scale is now down from 93 to 28. And again, you get some vibration, but the stress is way below the breaking point, the yield point. All right, so we go back to the oscillations. So my hypothesis was that the drop in current that occurs during the oscillation leads to the shock wave, or basically the fact that the current stops rising and then rises again is what leads to the shock wave. This was one of the last shots we took in January of 2020 after we had reduced the oscillations, but we were still getting a small dip. So I was saying this is a threshold effect. If we don't get any dip, maybe we can get rid of the shock wave. So that's basically where we are now. Let me just run briefly where we're going. Clearly, the big step that we need to take is to get this 3-fold increase in compression or in twist, which we expect would give us an 80 times increase in yield. Assuming, of course, we optimize the pressure, the deuterium-nitrogen mix, and the total angular momentum that we impose with the axial field coil. So our first goal is to get all the way up to 10 joules. So our previous record is a 1/4 joule. And with the beryllium, we were only at an 1/8 joule. So that's the big step, which we hope we can take with this experimental series. The fact that we had too short an anode, so, sorry, that probably affected our yield by a factor of 2. Why did we have too short an anode? Well, given the beryllium lead time, we had to order the material before we had the results from tungsten. And I was thinking we would have solved the induction problem before and have a shorter pulse length. In addition, there's rundown time formulas that I was using that did not take sufficient account of the length of our insulator. So that's why we ended up with a somewhat too short anode length. I think 12 centimeters, which is what we've got now, is going to be closer to optimal, and that should give us another factor of 2. The dual switches we anticipate will give us something like a 20% increase in current, but if we're back on the I to the 4th scaling, that's going to double our yield again. So we could get up, if all of this works, as high as 40 joules with this configuration. If we go to the full power configuration, which takes a lot more work because we have to put on 8 more switches, 8 more cables, quite a bit of manufacturing and assembly. We go up to full potential, then we get a 60% increase in current, and that would give us 8 times more yield, 300 joules with deuterium as the fuel. We hope this year to finally go to the PB11 with the decaborane fuel. So this would be double the burn rate for this fuel, 3 times as much energy per reaction. We expect higher compression with the higher Z. Quadruple the confinement time because we think the fusion energy will be feeding energy back into the field during the plasmoid lifetime. So the change in fuel will give us 100 times more yield. That'll get us up into the range where we're getting net energy. So that's the broad plan. And to summarize, right now, we have the highest fusion wall plug efficiency of any private effort. And I hope you guys will be checking into this claim. The highest confined T of any, this was of any private fusion effort, the highest confined T of any fusion effort, very low impurity, and we're getting ready, very close to a big test of breaking through the yield plateau and then going on to PB11. And possibly we'll have results while you're writing your report, but I've been wrong so many times, I won't guarantee it. So that's pretty much the situation.